So guys, we had spent the last section looking at the graphs of sine and cosine functions and how they're periodic functions because they cycle over and over. And kind of the same thing today. We're going to look at graphing the other trig functions. So we've gotten sine and cosine taken care of. What haven't we talked about yet? Tangent. What's another one?
Cotangent.
Cotangent.
Cosecant.
Yep. So we're going to look at graphing those right here and see what those characteristics are. Now there's a lot of core concepts in there today. I don't want to get too wrapped up in. You can read through those today. But pretty straightforward with this. Again, I think I wouldn't encourage this much in terms of just going to decimals and looking at this, but decimals is going to help you a lot with this, okay? Central question today, what are the characteristics of the graph of the tangent function? We're going to take what we learned from the tangent function and apply it to the other three, cotangent, secant, and cosecant today. So in order to answer our question, we need to be able to explore characteristics of tangent and cotangent functions. We're going to graph the tangent and cotangent along with graphing secant and cosecant functions. And honestly, kids, I mean, everything that we kind of talked about in the last section in terms of transformations is going to apply here. We're just going to start running into some little hiccups here. And one of the hiccups we're going to run into here is called an asymptote. You guys remember what an asymptote is?
Yeah.
It's like a line that a graph will approach, but it will never ever do what? Never cross it. So that's a line that a graph approaches more and more closely, but never crosses. Today an asymptote is going to show up in our four functions today when this is going to show up where function is, here's the big word today. Sometimes we get a lot of values on that trig table, but sometimes those values are not a number, they are what? Or undefined, okay? Guys, take a look. In fact, if you don't have your unit circle out, you may want to get that out right now, okay? So, if you look at like the four that we're going to deal with today, cosecant, secant, tangent, and cotangent, are there any values of theta where the function's undefined?
Yes.
Where does that tend to happen at?
0 to 1.
Okay, does it ever happen for sine and cosine?
Oh. Nope.
No, and remember the sine and cosine, we said it was periodic, they just kept on going forever. There was no breaks in them, okay? The other four are going to be grouped together today because they're going to have asymptotes. There's going to be time when those functions are what? Undefined, okay? Today we're going to start talking about the period of these four functions. You remember how to find the period of a sine and cosine? What was the formula?
2 pi over that.
Okay, today we're going to talk about the period in terms of these, but these are going to be defined as pi divided by the absolute value of b. Okay? So 2 pi over b is only relative for which two functions, my friends? Sine and what? Cosine. This cycle is going to be relative to all the others, okay? Amplitude, we know what amplitude is, but here's the deal. Amplitude doesn't really exist, okay? Because things are going to go on to infinity. So in this section, you'll be able to get an A value. You'll know an A value, but you're going to call it like a vertical stretch or a vertical shrink today. But with these four functions, there really is no amplitude. And the reason is, if I have a function that gets really, really close to an asymptote, it's going to continue to go up forever. Okay, it's never going to stop. There's never going to be a highest or lowest point. Okay. An x-intercept, you guys know what that is, right? Zeros are the points where the graph crosses the x-axis. We've talked about transformations all year long. It's any movement of a parent function to form a new function. You're going to hear me talk about local maximum and local minimum. Okay. Local maximums are going to kind of be like the peaks of a graph. And a local minimum would be the valleys of a graph. Okay? So if I had a graph kind of sketched like this, words like that. Maybe it's, how many peaks are there?
2.
Okay, we would say that this is a local maximum. In that area, that's the highest point. What would this considered? Local minimum. What would this point be considered? Be considered a peak. It'd be considered the local maximum. It would also be considered what we would call the global maximum. This is the absolute highest point. Okay, but in this area, what's the highest point? That. So peaks are considered local maximums, and valleys are considered local minimums. Okay, so those are things that we're going to come up with today when we're discussing transforming those 4 basic trig functions. So, questions about the vocabulary first to start today. You guys okay with it? Okay, let's roll. Second page. All right. Hey, it's working. That's awesome. Okay. You know, this core concept, I'm not going to get too involved in, okay? I'm going to kind of graph some stuff here. We can complete the table for y equals tangent of x, where x is an angle measure in radians. I'm not really going to plot the graph here. I'll put it in decimals here in a second. But guys, you're going to see, in fact, let me go to decimals and do this real quickly. So I can do it up here now. Okay. So we used to do it the other way. Okay. So your decimals, let's see, Carson people, all right. I'm going to start with the tangent function of x. Is that okay with you guys? Okay. Good thing about decimals is this. All your functions are listed right over here on the left. So they've even got the other 3 that are reciprocating. Got tangent right here. I'm going to put in my x. Now let's just talk about this real quickly. Okay, do you guys have your unit circle out by chance? Okay, I'm going to kind of hone in on this first. I'm going to kind of zoom in on this first one right here. Guys, first of all, does it look like things get repeated over and over again? Okay, so let me do this for you real quickly. Let's I want to go this way. I want to focus on that middle one, okay? All right. This graph is kind of goofy right here, but guys, what's one point that goes through here for tangent? 0, 0, okay? I want you guys to go to, let's see. Find me on the first quadrant. Go first quadrant, kids. Go to pi over 4 for me. What's the tangent at pi over 4?
1.
Okay, I'm just going to throw this in here. Tangent at pi over 4 is what value again?
1.
Let's see if I can get there right now. Pretty close there, right? Guys, take pi and divide it by 4 in your calculator for me. Okay, so I'm going to put some, add a table here. So I'm going to put pi divided by 4 in here. And you said the tangent at pi over 4 was what value?
0.79.
Okay, that's the pi over 4 value, 0.785 about. But the tangent of pi over 4 was what value?
Oh,
1, okay. Go to negative pi over 4, which would be the same as negative 45 degrees Negative 45 degrees would really be the same as 315 degrees. So go to 315 degrees, which is negative pi over 4 radians. What's the value there? Negative 1. Okay, now what I want you guys to do next is this. I want you to find me the first time that the tangent is undefined. Okay, so how many radians would that be?
5 over 2.
So I'm going to type in your x equal. And I'm going to give you the other one, x equals negative pi over 2. All right, I'm going to show you what I'm doing with these values. I'm going to have you write these down so you know these as references. You guys see the lines clear over here on the left? This vertical line on the left and this vertical line in the blue here. What do you think these lines are going to be called? Asymptotes, because that's the x values where tangent is technically undefined here. So today when we start talking about the tangent function, especially the tangent parent function, we're kind of looking at this from, guys, this is really how many radians to the left? Right up here. Negative pi over 2, ranging up to pi over 2. The distance from negative pi over 2 to positive pi over 2, what is that total distance, kids? It's like half pi plus half pi distance, isn't it? What's that distance right there? Turns out a cycle time or a period time for one tangent function is no longer 2 pi, it's actually what? 1 pi. Okay, and that's why we're going to talk about pi divided by b in terms of our cycle times today. But take a look at this, kids. It's pretty straightforward here. This is what I want for you guys to put down about that first thing with tangent function here. Okay, so go back to your notes. I'm not going to fill that table in. We kind of did that already. But I'm going to tell you right now, the values I want you to worry about are up here. Okay, and I'm going to tell you which values I want you to really focus on. Okay, at negative pi over 2, our function was undefined. Okay, I want you to put that value in there. Okay, at negative pi over 4, our value was negative 1. At 0, we were at 0. At pi over 4, we were at 1. And at pi over 2, we were at undefined again. Okay? There's a lot of stuff in here I'm going to read through quickly. I'm not too worried about what's up here, but it does talk about the characteristics of tangent and cotangent. It says the domain of a tangent is what? You probably see it on your paper better. The domain is all except for odd multiples of what? That means like 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on. Okay? Can't have pi over 2 because my function is what there, kids? Okay. The range of all is going to be all real numbers because it continues to go up and it continues to go down along the asymptote, so don't worry about that. It says the period of each graph is what? Pi. Okay? And then the x-intercepts for y equal a tangent occur at 0, pi, 2 pi, and 3 pi. Every pi, the x-intercepts are going to occur. You'll see that as we work through this, okay? So right down here, there's some more important stuff. This is the stuff I want you to pay attention to. The period of the vertical asymptotes of the graphs of y equals a times the tangent of bx and y equals a cotangent bx, where a and b are non-zero numbers, are as follows. It says the period of the graph of each function is what, kids? Okay, this is an important one. And this pertains to which function again? Or which two, I should say? Tangent and cotangent. Okay. The vertical asymptotes for y equals a tangent bx occur at odd multiples of pi over 2 divided by, pi divided by 2 what? I'll show you what that looks like here in a little bit. We're going to do ours a little differently here. We're going to kind of work with the parent one and then figure the rest out after that like we did. Remember in the last section, how many points did I really want you to come up with? 5. If I take a look at this table up here, for this parent function tangent, how many points did we really come up with? And we're going to talk about how you transform those here in a bit. So we'll do things a little differently there. This should be a divide sign right here. Pi divided by absolute value of b again. Okay, and then the thing I'm just going to tell you is this. We looked at the function already right here. This was the cotangent of x, or I'm sorry, this was the tangent of x. How's the cotangent of x change? Just got flipped, didn't it? Okay, it just got flipped, all right? So let's just run into example 1 here quickly on page 3. Kind of show you what the heck is going on, okay? So what they're really after here, and again, guys, this is, I mean, like I said, I'm not too excited about this section, but what I will tell you is I just want you to understand the characteristics of the shape of the graph, and I want you to understand what the A and B values do in terms of your asymptotes and what it does to your graph, okay? So it says graph what here, kids? Okay, so let's talk about this right here, okay? What would that 3 really do, kids? In the last section, we would have called that the amplitude. And we might call it the amplitude in this section only for these 4 functions. When it runs along an asymptote, is there absolutely a highest point, or does it just keep going on forever? Okay, so there's not really an amplitude. So it's going to take the points and really do what again? What did you say it was going to be, Cora? Did you say vertical stretch? Is that right? Very good. Okay, now, the next part of this would be, well, there's a 2x in there. That 2 is like the b value, right? Remember, the b value changes the period, right? But for our purposes with tangent and cotangent, we're not taking 2 pi divided by the absolute value of b. 1 cycle time is only pi. So here's the deal. For your new stuff right here, you're going to have a horizontal shrink by 1/2, which means your new period, kids, will be pi divided by what? What's your b value up here? 2, okay? All right, I'm going to sketch the right answer in here in a second, but I'm going to go to decimals and talk about what's going on here first. Is that okay with you guys? Okay. So what I want you to put up here with this tangent function first is the following, okay? I want you to make a little table up here. These are the points that you're always going to want to start with for parent function of tangent function, okay? So the first one we had up there, it might be x or it might be theta. We had negative pi over 2. We said that that was where the function was what for tangent? And we got that off the unit circle. Then the next one I wanted to use was negative pi over 4. We said that is going to be when the function's at negative 1. We said at 0, the function is 0. At pi over 4, we're back to 1. And where are we at pi over 2? Undefined again, okay? Those are going to be like your starting points. Remember how on the other one we said find your starting points after you figured the period and the midline and all that other stuff, and then you did a phase shift with it afterwards? We're kind of doing the same thing, but this time with the tangent function, what do I always want you to start with? Those 5 points right there. Okay, so we're going to come up with some final points down here. I'm going to tell you what those final points look like. Okay. Let's go to the graph right here. So with our graph right here, guys, do you agree that we've got a point that is negative pi over 4 comma negative 1? Okay, so this should get vertically stretched to what value? Multiplying by negative 3. How far away is this point from the x-axis, in other words, kids? 1 unit. So where's that going to fall down here now? 3. Okay, so now here's the next part of this. This point is also going to get horizontally shrunk. And when you shrink horizontally, you're moving closer to the x-axis, or I'm sorry, to the y-axis, or further away? This horizontal distance would shrink, right? So if I'm at negative pi over 4 units right here, what's half of negative pi over 4 units? What's half of 1/4? 1/8. So what's half of negative pi over 4? Okay, so I'm going to add another table here. I want to see if we hit these points. So I think another point that's going to show up here, guys, is going to be negative pi over 8. And then this is going to get stretched down how many units? By a scale factor of 3, so negative 1 should turn into what? Negative 1 would turn to negative 3, wouldn't it? Okay, so let me ask a question. See this green point right here? Does that look like half the distance away horizontally than this point is up here?
Yeah.
Does this look like it got vertically stretched down from negative 1 to negative 3? Okay, talk about 0, 0. What's the vertical stretch for 0? In other words, what's 0 times 3?
0.
What's half of 0?
0.
No, so that point's actually staying where? Right where it is. Oh, no. Okay, talk to me about this point. This point right here being pi over 4 comma 1. 1 would get vertically stretched to what? 3. How about pi over 4 right here for the x value? That's going to get cut in half for a horizontal. So pi over 8. Okay, so I have a question now. My undefined stuff right here was this. This happened to be at pi over 2. But when you horizontally shrink a graph, you're also horizontally shrinking where the asymptotes belong. So if this distance from the origin, where we start the graph, to this first asymptote is pi over 2, what's half that distance? So won't I have an asymptote at pi over negative 4? So let's just type this, x equals negative pi over 4. There's one new asymptote I think we're going to have. I also think x is, what's the distance from here to this asymptote over here? Isn't that pi over 2 units? Okay, so I'm going to go x equal pi over 4 here. There's my new asymptotes, this black one and this. I'm going to try and change the color on this. Orange lines are going to be your new asymptote here. Okay, and what was that function we were graphing, kids? Was it 3 tangent of kids? Quick question, did we hit the points I wanted to hit here, here, and here? Does it look like these are asymptotes right here and here in orange? Okay, so the thing I really want you to understand is this. When we start working with tangent function and they ask you to graph the first period of that tangent, the a value simply does what to the points? How? Or shrinks vertically, right? What's the b value really doing? Okay, makes sense there? All right, let me throw this out here at you then, okay? Where did I set my stylus down at? Ooh, here we are. So, right here, kiddos, if you have to graph some kind of a new tangent function, what points do I want you to start with? Okay, and we had the points, and I'm just going to plot them again. We were here, 0, 0. We were at pi over 4, comma, oh wait, at pi over 8, comma 1, which would have been right about here. And negative pi over 4, which would have been right about there. Your asymptotes, my friends, would have been at negative pi over 4 and pi over 4. By the way, from negative pi over 4 up to pi over 4, what's that distance?
8.
Not quite. Negative pi over 4 to 0 would be pi over 4, and another pi over 4 over would be
Pi over
2 pi over 4, wouldn't
4.
it?
So put those together.
2 pi over 4 reduces to what?
1.
1/2.
1/2 pi, right? Which is,
Pi over 2.
isn't that what we want our period to be right here?
Yes.
Okay, this is tricky, kids, but and I know it's very new for you. Come on. Yeah, you know, decide to quit working again, isn't it? Too good to be true. Come. Not responding. Yes, I can see it's not responding. Yeah, man. Well, here's this. Do this. Go ahead and put a vertical asymptote at negative pi over 4 right here, and one at pi over 4. And I've got this actually wrong. This negative 1 should have been at negative what?
Really?
This should have been at negative, this point should have been at negative 3. Didn't they stretch down 3 units, kids? Lordy, come on. So this should be right about here. This one should be right about here. And then your asymptote should go right over here. And then a sketch of your graph, tangent, kind of an S shape like this. Holy cow. Okay, so the next one I want to look at cotangent. What do you think I'm going to give you right off the bat, kids?
5 points.
5 points, okay? And maybe we should name our final points when we were down here, kids. Where did our new asymptote fall right here, kids?
Pi over 4.
Okay, so I'm going to put this XY table in here. So when we were at negative pi over 4 now, graph was undefined because everything was moved in horizontally. There was a horizontal shrink. We shrunk that distance down horizontally. Okay? Then we said this was, what was that, negative pi over 8, Cora? Is that what we said? I think that's what you said, right? And then this would be a negative 3. What's this point still?
0, 0.
0, 0. Next one was pi over 8, comma 3. And then finally the last one was, we got the pi over 4 again. And what happened to pi over 4 again, kids? Undefined. And that's what it should look like when you're done. Okay? Think about this, kids. Think about your y values. Think about your y values. I'm going to make this very simple for you here in a second. What did you say you were doing to your y values here? And your x values. Let's do the y values. Vertical stretch would affect y values, wouldn't it? Take all these y values times 3 up here, friends. What's 3 times undefined? Undefined still. What's 3 times negative 1? What's 3 times 0 still? What's 3 times 1? 3 times undefined is still what? You said the horizontal shrink by what here? Half. Ooh, well, let's see what that affects the x values, doesn't it? Let's see what happens here. Oh my gosh. Negative pi over 2 times half makes what? Half times the next one would be, half times 0 would still be what?
0.
See what I do in there, kids? Does that kind of click a little bit more that way to get those final points?
Yeah.
Okay, let's try another one. Let's get our first 5 set up. Let's do that for the next one without even having to graph it. Let's just see if we're right, okay? Guys, check out cotangent. I'm going to put the parent in for cotangent around 0. See what happens. All right, so let me get into decimals. I got a lot of stuff to clean out. Okay, in fact, I'm just going to open up a new window. And I'm going to type in decimals. Because I can. All right, so let's get the parent function for cotangent up there. By the way, when you guys go to lunch, I'm going to pause this. Remind me to start recording the last part of this when you come in. Can you do that for me?
Yes, sir.
Thank you. All right, so we want the cotangent of x this time, right?
I wasn't talking.
Guys, it looks like, you guys see my 0 right here? Guys, it looks like this function right here has a 0 at what value?
2.
Pi over 2 comma what?
0.
So it looks like I'm going to be able to start this at 0 and go all the way over to pi for this one, for cotangent. So the 5 values I want you to use for cotangent are the following. Are you ready? Let's get them established. I need your unit circle out, friends. Okay? Cotangent says the following. These are your 5 starters right here for cotangent. I want you to start at 0. I want you to use pi over 4, pi over 2, which we just saw in the graph was 0. I want you to use, oh, am I going to be able to fit that up here? I want you to use 3 pi over 4 and pi. Okay, so guys, at 0 for cotangent, what's the function say?
I don't have it.
Anybody have their unit circle out? Cotangent, 0
It's
degrees.
here. Yeah, it's undefined.
Undefined. Okay, this is where the parent function is, and undefined. How about the cotangent at pi over 4 radians?
What's the one furthest right? Is it just pi?
Just pi. Yep, Joe. You okay with that? I had to squeeze it in there. Sorry about
I
that.
didn't know if anything was on.
Can you read this one? 3 pi over 4?
Yep.
Okay. At pi over 4, what's the cotangent?
1.
1. How about pi over 2?
0.
How about 3 pi over 4?
-1.
And how about pi over 4?
Undefined.
Undefined again. Okay. Now, kids, is there an a value to this function?
No.
So it's basically 1, right? So the y values are really going to get multiplied by what value to end my final points?
1.
Right? How about the x values, though?
1.
Okay, the 4 here, my friends, is the horizontal change for x's, right? So it's going to be a shrink or a stretch horizontally. Shrink by what scale factor? 1/4. So we're taking all these times what, friends? Up top. Okay. So here we go. What's 0 times 1/4 going to be? 0. What's 1 times undefined going to be? So what's our first final point going to be for this new period?
0 undefined.
Okay, let's talk about the second one. What's 1/4 of pi over 4?
Pi over 6.
Pi over 16. And then 1 times 1 down here would be what?
1.
Okay. Pi over 4 times, oops, I already did that. What's 1/4 times pi over 2? Pi over 8. And then the bottom's still going to stay what? 1 times 0 here would still be what?
0.
Okay. Next point. I'm done talking.
3 pi over 16, -1.
And then my last one, friends.
Pi over 4.
Pi over 4 and what? Okay, so my asymptotes are going to happen where for this new function? Where and where? 0 and what else? Oh my gosh, 1 at 0 right here. And then 1 at pi over 4. Is that getting wider or is that getting really, really thin there? Okay. And I'm going to pause right there, kids. We'll look at the graph on decimals when you get back, and then we'll take a look at those. Okay, here we go. Kids, help me out. What were the new points we came up with then for this?
0 undefined.
Okay, so 0 undefined. Okay, so I'm going to put in an x equals 0 here. That's going to be one of our new asymptotes there. Okay. What was next?
Pi over 16, 1.
Do it.
Pi over 16. Oop. Next one. Put one at pi over 4, right?
Yeah.
Okay, I'll change that color. Okay, there's our two new asymptotes, right? And what was the new function?
Cotangent
No.
4x.
I like putting my drops on the
4x?
Yeah.
No, you.
How'd we do?
I'm just.
Right here in this first window here, guys. What do you think? Does it look like we got it right?
Yeah.
Say we're good then, right? Okay. Kids, do you get those 5 points I gave you to start with relative to tangent and cotangent? Okay, and then do you get how to move things around now?
Yes.
The A value multiplies to the Y. The B value is your scale factor for horizontal shrink or horizontal stretch for the X values. Okay. Let's take a look at these last two then, friends. So right here, the other core concept here, my friends, is this. We also need to take a look at the cosecant and the secant. So here we go. Now guys, the period of cosecant and secant today is what here?
2 pi.
Okay, the one that's going to be pi is going to be tangent and cotangent. Today, cosecant and secant, here's the deal. One whole cycle for this is going to be, you got to have the part that's down here for a graph and the part that's up here for a graph. Okay, that's one whole cycle time for those right there. Okay. So what I'm going to really jump into is this. You can read through all this right here. I think you'll understand when we get our first 5 points established. So take a look at what's in here about vertical asymptotes, about domain and stuff like that. Guys, what kind of point would this be right here?
That's the peak.
So we'll call the local,
Maximum.
and this right here would be a
Local minimum.
local minimum. Okay, so let's kind of see what we're up against here in this next one. Okay. Example 3, what kind of function is that, kids? Is that a secant graph? Okay, let me clean up decimals again. Throw in a secant graph up here. Show you what we're up against. Alright, so let's throw that secant graph in here. You guys know that you can find all of those by hitting functions, right?
Yep.
Go secant of x. Okay, here's my graph. Friends, add 0. Isn't this your first point right there for your secant graph? So it looks like your first parent function over here is going to range from, it's 2 pi long, so it's going to be negative pi to the left. Or pi over 2. Hang on a second. I'm sorry, I've got that wrong. We're going to range from, I guess we could. I think the points I want you to use for this are going to be, how do I want to do this? This would be negative pi over 2. And then we're going to range over to this one right down here, which is going to be, looks like 3 pi over 2. Pi over 2. Okay. Here's the values I want you to use when we're dealing with 5 points for this one. I've got to think 1, 2, 3, 4. Yep, got them. Okay. For your secant graph, this is the values I want you to use. All right. Okay, help me with your unit circle here again. I need 1 one to be looked up. Negative pi over 2. Negative pi over 2 is like negative 90 degrees. Negative 90 degrees, friends, is the same as 270. So find me the secant at 270. How about at 0?
1.
How about pi over 2?
Undefined.
How about pi? How about 3 pi over 2?
Undefined.
Undefined? Okay, now guys, the secant is a reciprocal of which function? Okay, I want to show you something right here. This here, my friends, is your secant function. Now, if I would type in y equals cosine of x, see how like these peaks and valleys? For a peak, for every peak of the cosine, what do you have for the secant here? A local minimum or a local maximum? Okay, so for every peak, there's a what here for this one? Okay, it's a maximum, but if I'm going from cosine to secant, every peak turns into really a what?
Minimum.
A minimum for the for the secant, right? Don't you have like a local minimum right here on the cosine function in blue, friends? Okay, minimums turn into local what for the secant? Maximum. So if you see a graph like this, you should just be able to draw, oh, that's there, this one's here, that one's there. See what I'm talking about there? Okay? And the same thing will be true of sine. So let's go and let me get this out of here. Okay? Back in the notes it says we want to graph one period of g of x equals 3 times what? 3 times the secant of x. So here's what's going to happen, kids. Is 3 going to affect the x values or the y values, my friends?
The X.
This will be a vertical stretch or horizontal stretch?
Vertical.
Vertical. So if it's vertical, it's going to affect the...
Wow.
Okay, so we're going to take everything down here times what?
3.
So what are my final points going to be, kids? Are your x's changing at all?
No.
So we're really going to end with negative pi over 2 to what? What's 3 times undefined still?
Undefined.
0 comma what?
3.
What's pi over 2 going to become?
Pi over 2.
And then 3 times your what? At pi over 2 you were originally,
Undefined.
so 3 times undefined would still be what?
Undefined.
What's your next point going to be?
Pi over negative 3.
Pi negative 3. And then
Undefined.
3 pi over 2 comma
Undefined.
undefined. Okay? And those would be 5 good points to start you on your graph here, okay? So if I go into decimals, I say, all right, where does this get shifted to? Our asymptotes didn't change at all this time, did they? So if I go, what was that, secant, was it 3 secant x, was that right, kids? Did this point right here get moved by a scale factor of 3 up to here, from 1 up to 3? Sure did, didn't it? How about from here to here?
Yep.
Okay. It all works out, okay? All right, so I think, guys, I think you can get an idea of sketching graphs from decimals. What I'm concerned about is this. Can you get the points? Now, I've given you the starting points for all these functions that I think we should use. Is that okay? Do you understand how to transform these points into these points given some of the parameters here, like the a and b value? Okay, let's look at one last one here, and we'll get you out of here for the day. Graph one period of 2 cosecant pi x. Okay, so let's look at the cosecant parent. The parent of the cosecant, let's see if it said anything. Doesn't so let me graph the cosecant parent. Oh, here comes the cosecant in parent form. I agree. Looks like the same thing, doesn't it?
Yes.
This one's going to go from 0 up to 2 pi, okay? So I'm going to need your help on the cosecant for the following. I'm going to have, let me get you the table for this that we want to change, okay? Table I want you to use to start for cosecant. Is it okay if I write down that this was a secant function up here, kids? And now I'm going to put the cosecant start down below here. Your cosecant start table. All right, I need your help. I want you to use these as your start values. It's going to go every pi over 2 units. Okay, friends, cosecant column is what you're in right now. Cosecant is 0 for me. Cosecant of pi over 2.
1.
Cosecant of pi. Cosecant of 3 pi over 2.
-1.
Cosecant of 2 pi. Okay, so let's get our final points in here, kids. There's a couple things happening this time. To get your new points for this cosecant. Okay, what's happening with the 2 right here, kids?
Vertical stretch.
Vertical stretch by
2.
2 and a horizontal. You guys agree a horizontal shrink by 1 over pi? Okay. So the y's are going to get multiplied by 2. We're going to multiply all the y's by 2. And we're going to multiply here everything by what?
1 over 5.
1 over pi. Okay, so what's 1 over pi times? Let's do the x's first. 1 over pi times 0 will still be 0, right? What are the pi values really going to do to each other?
Cancel.
So won't that become 1/2 for the next one? 1 over pi times pi would just be what?
1.
Okay, really the 1 over pi is just taking what out each time?
5.
Yeah, so this 3 pi over 2 will become what?
3 over 2.
And then 2 pi will become,
2.
okay. And down here we're going to multiply everything by 2. The undefined stay what? Okay. Let's see, this will be what value here?
2.
And this will be,
Negative.
now kids, I'm questioning a couple things here. Do you guys get the idea what cosecant and secant look like? That's a bunch of u's. One's a hump, one's a U shape. Okay, secant, cosecant. Do you get like the tangent, cotangent are kind of squiggly S's there with asymptotes? Okay, if you can come up with 5 points like that, then use decimals to sketch some things in there. If you have to do it, I think you should be in pretty good shape. But really, we're talking about A and B. A is going to be some kind of a vertical change. The B is going to be some kind of a horizontal change. Are you guys clear on the points I want you to start with for each of those 4 trig functions? Okay. Again, I know this is very new for you. You'll get some time to work on this tomorrow. I did send the new online out, so if you get a chance to start looking at that, I would. Let's not do it until Tuesday, April 6th.